Hello, this is Mr. Huff. Let's take a moment to think about the Earth's atmosphere and what this has to do with flight. So first of all, the atmosphere is made of a combination of gases. It's mostly nitrogen. 21% of it's oxygen, and whatever's left is trace gases like carbon dioxide is a trace gas. It's important to us because it sustains life and it protects us from solar radiation. Without the atmosphere, we would have really, really terrible problems with ultraviolet radiation and that sort of thing. The atmosphere is 60 miles thick. If you were to compare the Earth to a baseball, the thickness of the atmosphere would be like a saran wrap wrapped around a baseball. So close to the sea level, we have the troposphere and then the tropopause. The stratosphere, which is this zone here between these two lines, and the stratopause, which is this line. It's a level. What's happening at the tropopause and the stratopause and the mesopause is this zone is ending and it is a level. Have you ever seen a thunderstorm? We have a lot of thunderstorms in Texas. And have you ever noticed far away the top of the cloud is flat? And that's because it's hitting the one of these pauses. So it goes up to a certain height and it can't go any further. It hits that level. So above the stratosphere, and well, actually, that would be the tropopause where clouds end. Then we have the stratosphere, the mesosphere, and the thermosphere, and then you have the pauses in between, the mesopause, stratopause, and tropopause. I would suggest recording this diagram in your handy dandy notebook, but I'll give you a notes assignment with this as well. Most flight occurs in this zone right here in the troposphere and stratosphere. So this diagram is kind of showing the idea of how air has weight. So if you put your two thumbnails next to each other in front of you and look at that area of your two thumbnails together, there are over 14 pounds of air on top of those thumbs. That's the pressure. So one of the things you'll see here is this 101.3 kilopascals or 14.7 psi. That is going to be what we refer to as standard pressure. So that's the idea. Look at your thumbnails. There's almost 15 pounds of air resting on those two thumbnails. Standard pressure and temperature, these are things you will need to know, and we'll talk about them when we get to the formulas in just a moment. But 15 degrees Celsius and 101.3 kilopascals and 59 degrees Fahrenheit and 14.7 psi. Those are standard temperature and pressure, and that's what we use to do calculations and measurements. This diagram is a little bit confusing. Consider this a graph right here. So what do you see happening to temperature as the thousands of feet decrease? So as you increase, yeah, this is really confusing. Starting from sea level, as you increase, the temperature decreases. As you start at sea level and you increase altitude, pressure decreases. So it's a linear relationship until you get outside of the atmosphere. So 2 degrees per 1,000 feet and 1 inch of mercury per 1,000 feet. All right, so here we see a couple of formulas. The first one is to calculate temperature by height. So to calculate the temperature at a given height, and this is in comparison to standard temperature and pressure, you take 15.04 degrees Celsius minus this conversion factor, 0.00649 degrees Celsius per meter, and then your height in meters. Okay. The next formula is about pressure calculation. Pressure is related to temperature. So everything you see here is a constant except for this number, temperature, which you get from this calculation. So these two are tied together. So to calculate the pressure, you take this standard pressure, 101.29 kPa. All of this inside the brackets is raised to the 5.256 power. Inside this, you're converting temperature to Kelvin. So you have the temperature, which is in degrees Celsius, plus the conversion factor for Kelvin, and then the degrees Celsius cancels out, and you're left with degrees Kelvin divided by this value, which is Kelvin. So that will spit out the pressure at a given temperature. A little complicated, but it's not a bad calculation. We'll get to that later. The density of the air changes based on pressure and temperature. As you increase altitude, the density is lower. As you decrease altitude, like at sea level, the air is dense, and as in the mesosphere and thermosphere, it's very, very thin. So this is a formula for calculating rho, which is density. It's important to pay attention to the units. I'll talk more about putting your formulas down, but rho is equal to density, which is kilograms per cubic meter. These units are important. Make sure you use the right units or it will not work. Temperature is going to be in degrees Celsius, height is going to be in meters, and pressure is in kilopascals. So to find the density of the air, you take the pressure and divide it by these conversion factors, which the only number you put in here is temperature. We use height. And remember, here we calculated the pressure and the temperature, and then you use that pressure to find the density. So this can turn into a lengthy calculation. Mount Everest is 8,848 meters tall, or 29,000 feet, and this is similar to the altitude at which jet aircraft fly. They won't fly over Mount Everest because if they were to crash up there, it would be really hard to go get them. So there's altitude is around 10,000 feet, where if you don't have oxygen, some bad things happen, and I need to put in here about hypoxia, so we'll share that. So, but aircraft that fly at these altitudes like 29,000 feet and 40,000 feet and 14,000 feet, you have to have additional oxygen. So you may have seen pictures like this. This occurs when the atmospheric conditions are just right, and when an aircraft breaks the speed of sound, you get this bell cloud that forms around them. So once you pass 250 miles an hour, you start having serious resistance from the air due to the compressed air speeds. You can see this diagram here is a aircraft model in a wind tunnel at supersonic speeds, and you start getting these shock waves coming off of the aircraft, the leading surfaces and that sort of thing. So once you go above the speed of sound, now your craft is moving faster than the sound it's producing, and that's what causes the sonic booms. So let's talk about mach, which is a measurement. So basically you're looking at a representation of how many times the speed of sound are they traveling. The problem with that is the speed of sound changes at the sea level. It's 761 miles per hour, but if you remember Chuck Yeager in the X-1, he broke the speed of sound at 700 miles an hour, so how can that be? Well, the thing is, it's tied to density and temperature, so there's more factors in there that determine the speed of sound. So he was flying at a much higher altitude with a lower density air, and the speed of sound is not as high at a higher altitude. So these are the things you need to know about Mach. If you are below Mach 1, which is Mach 1 is the speed of sound, so you're subsonic. If you're between Mach 1 and Mach 5, you're supersonic, and if you're from 5 to 10, you're hypersonic, and if you're Mach 10 to 25, you're high hypersonic. Right now, the Navy is working on railguns, which will launch projectiles between 5 and 10 times the speed of sound, so Mach 6, 7. They're hoping that they can use this as a weapon, so that would launch a high speed of projectile without any propellant is what they're trying to do, and that makes it a lot safer in their ships. Most of the supersonic aircraft like the SR-71 Blackbird and those like the Tupolev and the Concorde supersonic jets, they like to fly at really high altitudes so that they don't have as much air resistance. The SR-71 Blackbird is designed where as things heat up, they expand, so it's designed such that all of the metal plates come together when it's at cruising speed and really hot. So when that thing is on the ground, it rattles and fuel is leaking and it looks like a mess because it's shaky, and that's because the metal is going to expand as it gets hot. And that thing gets really hot. So as it's flying at its cruising speed, the whole craft is really hot, and all of the metal expands, and all those gaps close, and all those things seal up. So, all right, that's all I have for now.